Okay, everyone. So there's a differential equation that should look familiar to you. We solved it in Chapter 3 as a first-order linear differential equation, and we did it analytically. Remember, that's one way to solve things. And then we did it in the previous section, 4.1, graphically. That is, we just drew a picture that looked like it was a reasonable picture of the solution, and that's a way to understand and get a solution. And then today we're going to do it yet the third way, which is numerically, okay, which means that we use numbers. We put in numbers and calculators and things like that and plug and chug, and we get numerical answers. So you'll see how that goes in a few minutes. Okay, so this is section 4.2 in which we do it that way. And let me just stress again that we already know the solution of this thing. There's the general solution. If we have this differential equation and we have the initial value problem, given that y of 0 is equal to 1, then this is called an initial value problem. Then we can solve for c here. In fact, let's go ahead and just do it right now as long as I mentioned it. Y of 0 is equal to 1, and if you stick in a 0 for x, you're going to get c times 1 is c, minus 0 minus 1, and so you're going to get 1 is equal to c minus 1, and so obviously c is equal to 2. So here's the solution right there to that initial value problem. That's the exact solution. Once we have that, there's no need for anything else. So I'm using this to illustrate this numerical method, not because we have no other way to do it, but just because once we get the answer to this thing, we'll be able to compare it with the true answer, and we'll see how far off it is. But in general, the place where you would use this would be in some situation where you can't, where you would use this method in some situation where you can't find the analytical solution. So for example, if you had x plus y squared there, then it's no longer a linear first order dE, and so the method that we had from chapter 3 wouldn't work, and so you would have to use this method. This would be really the only one available to you if you wanted to find the value of the graph of the solution, or the value of the solution at some point. So say, for example, say that we have this. Let's go back to the one we were working on. Say we have this particular differential equation, and we know that at 0 the value of the function is 1, and we want to know what will the solution be at 1/2. What will it be at 1/2? And of course we can find the answer here, but if we didn't have that, then how would we go about trying to get it? Okay, so that's what we're gonna get. And before we do that, let me remind you of something that you should have in your bones. You should understand from an algebra course. Suppose you have, say, the graph of y is equal to, what does that look like? Maybe 3x plus 1, something like that. Maybe 3x plus 2. Let's make it 3x plus 2. So this is the point 0, 2 right there. And if you go 1 away, then you're going to be at the point what? 1, 5. If you go 2 away from the origin, then you're going to be at the point 2, 8, and so on. Okay, so there's a line that goes through those points. Now, here's what I want to just really stress with you. What's the relationship between the change in x, the change in y, and the slope? And hopefully you're laughing at me saying, well, of course, I know that. The slope is just equal to the ratio of those two things, right? It's this divided by that. But for some reason, even though students know that, it doesn't occur to them that all they have to do is multiply through by this denominator, and then they get this relationship. So what's this one saying? This is saying, hey, this one is saying if I know the change in y and I know the change in x, I can find the slope. This one is saying if I know the change in x and I know the slope, I can find the change in y. Agreed? So here, if this change in x is 1 and the slope is 3, then the change in y is going to be 3, right? That change in y is going to be 3. If the slope is 3 and the change in x is now 2, then what's the change in y? Well, 8 minus 2 is 6, right? Which is clear from this as well. The slope times the change in x gives you the change in y. So as I say, that's super important. Hopefully that you're laughing at me saying, well, of course I know that. But I just know from years of teaching that sometimes people don't. So you need to have that understanding now before we go on with what we're going to be doing. Okay? So if you remember from our previous lesson, we had the solution, the graphical solution of this thing looked kind of like this. Kind of like that. It kept going steeper and steeper and steeper as you went. Okay? That was the rough idea for the solution. And what we're going to do now is to try to find what are some points along that graph. And we won't be able to find them exactly, but we realize that. We're going to instead just try to get them roughly. And the very first thing I should do is to make clear that at the point 1 right here, here's the point 0, 1, that the slope there is going to be 1. So say it looks like that instead. Okay, so the graph looks maybe something like that. Okay, so what do? Well, here's what we do. This is our initial value. So when x is 0, here's the x-axis, here's the y-axis. When x is 0, we know that the y value is 1, which is right there. So let's go ahead and fill in those points. There's 0 and there's 1. And so given that, what's the slope of the graph then at this point? Well, this right here gives us the slope, right? What does it say to do? You add the x and the y coordinates together and that gives you the slope. So 0 plus 1 gives you a slope of 1, and so that's going to be the slope. And now that we have that point, we're going to move over a little bit and see what happens when we take a little step over, and what we're going to step over so that the new x value is now going to be 0.1, and we need to get an approximation for the new y value. Now, what do I mean by that? There's a relationship between discrete and continuous things that's right at the heart of calculus. Think about the integral, for example. If you want to find the area underneath the curve from, say, A to B, how did we learn to do it? What do? You break this thing up into little subintervals. They don't have to be equal size, but they may as well be, if you can kind of do that. And then what do? Then we say, okay, on this first interval, let's just assume that the height of the function is always the value at that left endpoint. And we'll just keep using the left endpoint over and over and over again, like that. And then we'll find the areas underneath these rectangles. And once you find the areas underneath these rectangles, that's going to give you at least an approximation for the area underneath the function. Agreed? And so that's, of course, at the heart of the idea of the integral. And then the other thing that's right key is that if you want to get a better approximation than this, you can generally get a better approximation by breaking this thing up and making the steps smaller. So now it looks like this instead. So you have this, and then you go just there to there. And then this one goes from here to here, but then this one goes from there to there. And this one goes there to there. But look at there, you're leaving off all that extra stuff. You're closer than you were before. Let's look at these two right here. You're going to go there, and then you're going to go there. So you're better off when you take smaller intervals. Okay? And of course, that's what led to the idea of the derivative as well, right? Well, how did we find the idea of the derivative? We went like this and we said, okay, let's take the slope of a secant line, which is something you can do in algebra, and then we'll do what? We'll take the limit as that becomes a smaller and smaller little interval, and we'll finally take the limit as this point gets pushed into this one, and that gives us the value of the slope of the tangent line. So now we're going to kind of go in the opposite direction. We already know that the solution might look something like that, and we're just going to settle with the fact that we're just going to pretend that this thing doesn't curve up, that it just continues moving with slope 1 from this point. We know the slope right here is 1. See that? The slope is 1 right there. We know the slope is 1. And so the point is, as soon as I start moving off this line at all and just go straight along this tangent line, I notice that I'm no longer on the graph. I'm no longer where I want to be. But hopefully, at least I'm close. And the smaller of a step I take, the closer I will be. So I don't know how accurate this actual picture is, but as soon as I move 0.1 away, I notice look like I'm going to be a little bit below it, but at least hopefully I'm close. So at this point, let's pretend that this point is another point on the graph. What do? We say, well, this new x value is going to be the old x value, which is 0, and then I took a step. Here's my step right here. My step is 0.1. So I take a step of 0.1, and that's going to be the new x value right there, 0.1. Now is where we need to apply what I just taught you about slopes. What's going to be the new y value? Well, it's going to be the old y value. Here's the old y value, which is 1, plus it's going to be this extra amount. And that extra amount is just the slope times the change in x, right? If I take the slope at this point right there times the change in x, that's going to give me the change in y. So there's the change in y right there. So the new y is going to be the old y plus the change in y. So the old y is 1, and then the change in y is going to be the slope right there, which is 1. That slope is 1, and the change in x is 0.1, and you multiply those together and you get 0.1. So it's going to be 1 plus 0.1, which is of course 1.1. So there's your new point, which we're going to pretend is on the graph, even though we know it's actually a little bit off. Okay? So where do we go from there? We do the same thing. We say, okay, now what point are we starting at now? We're starting at 0.1 for the x, and the y value now is going to be 1.1. Okay? So we're at this point right here, and we ask the question, what's the slope of the graph of this thing going to be as it goes through this point? Well, if x is this value and y is this value, what does this say to do? To get the slope, you add them together. So 1.1 plus 0.1 is going to be 1.2. So there's 1.2. Okay, so now we've got everything we need. So now we take a step in this direction again. So we first take a step of 0.1. So this is now going to be 0.2. There's our new x value. And the new y value is going to be the old one. We're starting right here. We're starting right there, which is 1.1. And now what do we have to add to it? What do we do? Well, we do the same thing as before. What do? We say, okay, the slope is 1.2. You multiply the slope times this interval, which is 0.1. And when you do that, that's going to give you the new change in y. So there's the old y value right there. Here's the change right there, and you add those together, and you're going to get what? It's going to be 1.1, and then if I move this over, it's going to be 0.12, so it should be 1.22. Like so. Okay, let's make sure I'm staying with the same numbers I had before. Okay, very good. Okay, where do we go from there? Well, let's take another step. Okay, so now we're at 0.2. So here's where we are right there now. Notice that we're a little farther away from the graph, and the y value is 1.22. That's that value right there, because we added the change to the old one. So there's where we are. What's going to be the slope? What's going to be the slope of the graph that goes through of the solution that goes through this point? Well, same as before, you add the x and the y value, so it's going to be this plus this, which is going to be 1.42 right there. So now we again have everything we need. And so now I'm going to be running out of room here, so I won't continue the picture. But now we can again move over a tenth of a point, tenth of a unit. So we're going to get 0.3. And how do we get the new y? We take the old y, and what do we add to it? We add this change. How do we get the change? We get the change by taking the slope times the little change in x, which is 0.1. And by the time you add that together, let's do it, 1.22. And if you move the decimal place, you're going to get 142. You're going to get 1352. Make sure I'm same as, 1362. Oh, 6. 2 plus 4 is 6. Very good. Okay, so 1.362. See that? Okay, let's keep going. Now I'm going to have to erase my picture just in order to get enough room to continue on here. So here's 0.3. The y value where I am is 1.362. The slope there is going to be what you get by adding those together. So it's going to be 1.662. Now I move over and get 0.4. And then what do? I take the old y value, 1.362, and I add to that the change. And the change is the slope times the change in the x coordinate, which is 0.1. So what do I get? 1.362. That's going to be 1662. It's going to be 28251. 15282. Yep, that's what I got. 15282. Like so. Okay, let's go one more since we're interested in what this value is going to be. So here we are at 0.4. The y value is 1.5282. The slope there, now you add these two, it's going to be 1.9282. And now here's the one we want. The new y value is going to be 0.5, which is our 1/2, of course. And then the new y value is going to be the old y value. Here's the old y value, 1.5282 plus the slope, 1.9282 times 0.1, and we get what? 15282, and we move this decimal place over. Did I do that right? It's going to be 2, 0, 1, 2, 7, 1. 172102. Yep, that's what I got right there. So there it is right there. There and there should be something close to the actual value, because I kept moving farther and farther away as I took these steps. I'm going to be farther and farther away from the value on that graph, but let's see once how close we are. So if we go ahead and put this into the calculator, put in 1/2 there for x, let's see once what we get. I'll do it, and I get 1.7974. So sure enough, the true value is larger than the one that we got by way of an approximation. See that? It's concave up, and so you can argue, should hopefully be able to see that for something that's concave up, this approximation is going to be less than the true value. Okay? So there you go. So that's the idea. And again, to emphasize that if you want to get a better approximation, you could just, instead of using a step size of 0.1, you could use a step size of 0.01, right? Then all these little, just like using smaller step sizes to find the area, you're going to get something much better. The problem is, then you would have to go through this, instead of 5 times, you'd have to go through it 50 times. So I wouldn't want to go through that 50 times, or if you want to make this 0.001 500 times. But computers love doing this sort of thing. That's what they're built for, right? That's what makes them happy in life. And so if you use Excel or whatever else to form a little program like this, you can do it, and you can get it to give you an approximation. So that's what I ask you to do in the textbook, is to see once what happens when you alter the step size a little bit. And also the other thing to do is to say, okay, as I say, this was fine on this particular problem, but we really didn't have to do it because we already know the real answer. But a problem like this, then there is no solution that you can get using the methods that we had for first order linear, since this one is no longer linear. And so then if you wanted to know what the solution was going to be at the 0.1/2, you would have no real choice except to use this sort of a method right here. Okay? So it's called Euler's method. It's called Euler's method, spelled like that. Okay? If you know how to pronounce that correctly, you'll impress any mathematician. And once you become familiar with Euler, you'll see his name just throughout mathematics. He just wrote lots and lots and lots of papers and was influential in all sorts of areas of cut off right at the very end, all sorts of areas of analysis and probability and things like that. So there you go. So this finishes all that we're going to do with regard to finding solutions to first order differential equations. Okay, what did we do? We looked at separable, we looked at linear, and we found ways to do it numerically and graphically. And so that's basically any textbook you pick up. That's what they're going to show you. So now we go on to second order differential equations, in particular second order linear differential equations. We're going to limit ourselves just to linear, and that's a very important area because there's lots of things in the physical world which can be modeled, can be described with second order linear DEs. But in order to understand that fully, we need to have a little recap of linear algebra. So the next thing in the book, you'll notice chapter 5 is called a linear algebra interlude. Interlude is a musical term meaning a little break. And so we're going to break from DEs for momentarily and do a little review, or if you haven't had it yet, learning for the first time of some basic linear algebra stuff, vector spaces. And once we have that, then we will jump into second order linear differential equations. So that's what's coming up. We'll see you then.